Welcome in. We get to start a new chapter today on molecules and compounds. Our learning objectives are to describe the difference between atomic and molecular elements, describe the difference between ionic and molecular compounds, and we'll predict whether compounds will be ionic or molecular. Let's start here with some background. We learned about our atoms and our elements in the previous videos. But as it turns out, what we encounter in the real world is mostly compounds, more complex structure formed by fusing, chemically bonding multiple atoms together. We can represent these molecules, these compounds, with chemical formulas. In our chemical formulas, which maybe we've seen out in the real world as well, we need to represent what elements are present and how many of each element are present. In our chemical formulas, we have subscripts that refer to the element symbol right before it. Here in this formula H2O, that 2 is attached to the hydrogen, telling you that there are 2 hydrogens. The oxygen afterwards does not have a value after it, which means that there is just one of those oxygens. When you change these subscripts, when you change your chemical formula, you're going to change what compound you have. And different compounds will behave very, very differently. Here we have carbon monoxide on the left, CO. On the right, we have CO2, carbon dioxide. Both of these are maybe not the best gases to have around, but while CO2 is a greenhouse gas and going to cause global warming maybe sooner rather than later, carbon monoxide is poisonous to humans on the scale of minutes and hours. When we write our chemical formulas, there is a specific order. We want to start with our metallic elements first, followed by our other non-metal elements. In general, on the periodic table, this means we start at the bottom left and we move towards the top right when we're deciding which elements to start with in our formula. There's a helpful table here on this slide that will tell you exactly the order for some of the more ambiguous choices that you might have to make. But this is the general trend. Start at the bottom left and work your way towards the top right. We can do this first example. If we have 2 silver atoms, silver is the symbol Ag. We need to have a 2 to the bottom right. And we have 1 sulfur atom. Sulfur is the symbol S. Since there's just one of those sulfurs, we don't need to include that subscript. In fact, we should not include that subscript. We want to take a minute and point out some interesting cases that will come up a lot. We can have what are called polyatomic ions, which exist as a unit, which exist as a group. Here we have, on our slide, we have NO3. This is 3 atoms attached to our nitrogen. In fact, we have nitrogen surrounded by 3 oxygens. And as a group, this carries a charge of -1. So ultimately what we have is this bundle of 4 atoms moving around as a unit, and as a unit it carries a charge. That's why we call it polyatomic ions. Multiple atoms that act as a charged unit. To give whoever is reading our chemical formulas some intuition about that polyatomic ion, we like to group it in parentheses when we write the chemical formula. Mg parentheses NO3 2 means that we have two of those units combining with one of our magnesiums. Here is what our chemical formula is describing. I said we like to use parentheses for those polyatomic ions. This is only needed if we have a number outside of those parentheses. If you have only one of those NO3 units, then you don't need to have a parentheses at all. For example, if you have sodium instead of magnesium, we can just write NaNO3, no parentheses needed at all. Here's that chemical formula broken down a little bit. We can try to interpret this. MgNO3 parentheses 2 contains 1 magnesium atom, 2 nitrogen atoms, and 6 total oxygen atoms, because this 2 has to talk about everything inside the parentheses. If you want to see the actual picture of what this maybe would look like, we have 1 magnesium and then we have 2 of these NO3 units. So in total we have, 1 magnesium, 2 nitrogens, 6 oxygens. We can try to count those up. We have a number of ways that we can represent our chemicals with our chemical formulas. What we've been talking about so far is our molecular formula, telling you exactly how many atoms of each type are in that molecule. Sometimes we don't have as much information as that, or maybe sometimes we don't need as much information as that. The empirical formula is simplified to only telling you the ratio. What is the simplest ratio of elements for each other? We can also display our chemicals with maybe extra three-dimensional information. If you have a structural formula, you can show where the chemical bonds are, or maybe the three-dimensional shape, or maybe how much space these atoms actually occupy in real life. We're going to continue our categorization techniques, zooming in on our elements and our compounds from our previous lessons. As it turns out, our elements can be two different things, and our compounds can be two different things. Let's start with our elements. The elements show up on the periodic table, and some elements exist as just single atoms, maybe in the form of a solid or a liquid or a gas, but the simplest unit is just a single atom. In our picture, we can see mercury as a liquid. We have those atoms packed together but able to move around past each other. But our smallest unit is just a single atom. You could also have a balloon of helium, where you have individual helium atoms bouncing around inside of that balloon. We can identify, oh, there's a single atom as our smallest basic unit. In contrast, some of our elements do not exist as single atoms, but instead exist as groups that are bonded together. This is most often two atoms bonded together, but there are other examples as well. It'd be a good thing to do to remember these diatomic molecules, these elements that show up as exactly two atoms bonded together. If you see something like chlorine as an element, chlorine exists as Cl2. We have chlorine not as a single atom, but it's actually this pair of atoms chemically bonded together. Likewise with all of our other elements in group 17. The other three that we need to know, hydrogen, nitrogen, and oxygen. Hydrogen, nitrogen, oxygen, and those halogens exist as diatomic elements if you find them out in the wild as elements. Here is our periodic table highlighting where those are. Everything here in group 17 exists as that diatomic element when it is an element. Nitrogen, oxygen, and hydrogen as well. Moving on, we can think about our compounds. We said compounds also can exist as two separate forms. Our two unique things are molecular compounds and ionic compounds. Molecular compounds form when we have all non-metals. And our molecules are formed using what we call covalent bonds, which we'll learn much more about in the coming weeks. A distinguishing characteristic of our molecular compounds is that we do have simple basic units of individual molecules. If you're looking at something like water, H2O, you can find individual units of H2O out in that sample. This is not always the case, and we can look at the alternative right now. Ionic compounds do not exist as that discrete unit. Let's rewind for a second. Ionic compounds form when we have ions. These ionic compounds form because we have positive and negative charges that are attracted to each other, and they can form a nice bond based on their electrostatic forces. A rule of thumb is that we have a metal and a non-metal combining to form ionic compounds. There is an asterisk here. We also start to see ionic compounds when we have polyatomic ions. In these ionic compounds, we get to have lots of positive charges and lots of negative charges. We do not have to combine into simple small molecule units. Instead, we get to form these repeating patterns where everything is attracted to everything that's around it. Our negative charges get to be surrounded by positive charges. Our positive charges get to be surrounded by negative charges. Here's our picture. If this looks familiar from our crystalline solids, that's because it's the same picture. These ionic compounds like to form these crystals, these lattice structures of repeating patterns. Because we don't have a molecule as our smallest unit, we can describe our ionic compounds using formula units. What is the simplest repeating pattern inside of our crystal? This formula unit does have to be neutral. It does have to have a total charge of 0. We can do some example problems classifying our elements and our compounds. I'm going to start with KNO3. This is not an element because it has multiple elements in that formula. This has to be a compound. And moreover, we can see that we have a metal combined with a polyatomic ion. This has to be ionic. So we can say that we have some ionic compound with KNO3. Our next example is chlorine. Chlorine is on the periodic table, so it has to be an element. For our elements, we either have atomic or molecular. Chlorine actually exists as Cl2, which we get to know. And so this is a molecular element. Finally, one last example, we have Au. This is also an element. It is on the periodic table, and it is just a single type of atom. Au is not one of our diatomic elements, so instead it has to be atomic. It exists as individual gold atoms, probably as a solid at room temperature, but we do have those individual atoms that are identifiable as our smallest unit. We have a number of other practice problems on this slide. Take a moment, see if you can write down some good answers. There we go. We can describe the difference between atomic and molecular elements, ionic and molecular compounds, and we can predict whether a compound will be ionic or molecular. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.